Okay, so I just wanted to share some of the answers to the Microsoft forms that you completed on the Gibbs Free Energy 2, the AfL. So the first question, you can see here we're going from a solid to a solid and gas. So the delta S will be increasing. We can see that delta H here is positive. So if we consider the expression delta G equals delta H minus T delta S, delta H is positive. We know that delta S is going to be positive. So in order to make delta G negative, because that's when something's feasible, we need to make this term bigger than that term, and it will only happen when the temperature is as high as feasibly possible. So C is the answer. It's not possible at low temperatures, but it is at higher temperatures. So C was the answer, and that was the explanation for it. So really well explanation, good explanation given there. Number 2, again, if we consider delta G equals delta H minus T delta S, we can see here we've got 3 moles of gas going to 2 moles of gas, so actually delta S here is going to be positive, which is is going to be negative because we're losing entropy. So this whole term here is going to be positive. We've got a delta H of negative, so actually what we want is that temperature there to be as low as possible. So the answer to this is D. It's feasible at low temperatures but not at high temperatures. Okay, number 3. Again, we're going to consider delta G equals delta H minus T delta S. We can see here we've got a liquid going to a liquid and gas, so delta S is going to be positive, so it's going positive. We can see delta H is negative. This whole term here is always going to be negative, so regardless of the temperature, we're always going to have a negative delta G. So the answer to this is it's feasible at all temperatures, which is A. And then number 4, again we consider delta G equals delta H minus T delta S. We can see here we've got a solid and a gas going to a gas. We've got 2 moles of gas and only 1 mole of gas here, so delta S is going to be negative. We know we've got a positive delta H, so this term is always going to be positive, that's always going to be positive, so actually this is not feasible at any temperature at all. So it doesn't matter what temperature T is, this term is always going to be positive. So the answer to this is B. Okay, so we've got the next question here, and it's saying that hydrogen is manufactured by heating methane with steam, and that's all it gives you. So you need to calculate delta G, but actually you need an equation, so you're going to have to write one. So methane, even if you don't know, have a look in this table here, and you can see methane is CH4, so it's telling you that methane is heated in the presence of steam, which is water, H2O gas, in the presence of a nickel catalyst. You can put that on the arrow if you like, and that's going to give you hydrogen. So we know we're going to get hydrogen. What else are we going to get? We'll have a look here, and the only thing in here is carbon monoxide. So carbon monoxide is the other thing we've got. We do need to balance this equation up. 1 carbon, 1 carbon, 1 oxygen, 1 oxygen. So how many hydrogen have we got? 4, 5, 6. 6, so we need 6 on this side, so that will be 3. Okay, so that's the first thing, to be able to write your equation. Alright, so by calculating delta G, so we can always, delta G equals delta H minus T delta S. Do we have a delta H? Well, it's not given as one, but it's given these, so we're going to have to calculate it. Has it given us a delta S? No, but it's given us these, so we'll have to calculate it. Has it given us a T? Yes, we have. Okay, so we need to be able to calculate delta H and delta S. So to calculate delta H, that's the delta H of the enthalpy of reaction, we know it's going to be the sum of the enthalpies of the formation of the products take away the sum of the enthalpy of formation of the reactants. So we're going to have to do that. So we can see that the products are carbon monoxide and hydrogen. So the enthalpies of carbon monoxide, we only have 1 mole, is minus 111. The enthalpy for hydrogen is 0, so we don't need to include that. Take away the sum of the reactants are water and methane, and we only have 1 mole, so this is minus 242 and minus 75. Okay, I'll just simplify that for you and work this out. Okay, so I've done that for you. So minus 111, take away, simplified this, it's minus 317, and we know a minus and a minus is a plus, and when we do that equation, then delta H of the reaction is 206, and we just have to remember it's kilojoules per mole. Okay, the next part, so we've got delta H, we need to work out delta S. So delta S for the reaction is the sum of the entropies of the products, take away the sum of the entropies of the reactants. So if you can remember that, SPAR. So entropy is the products, take away the reactants. Okay, so we have that here. So the entropy of the products are carbon monoxide, that is 197.6, plus hydrogen is 130, and I've got 3 moles of that, 130.6. Take away the reactants, I've got water, which is 188.7, plus methane, which is 186.2. Okay, so I'll go ahead and I'll simplify this and I'll show you the answer. Okay, so the delta S of this, when I've simplified it, this bracket here is 589.4, this bracket here is 374.9, and so the overall entropy change is 214.5. So now we just have to remember that's joules per Kelvin per mole, this is kilojoules per mole. So all we need to do now is to substitute these figures into that equation. I don't have any space below here, so I'm going to do it at the top. So delta G equals, delta H we've got as 206, so that equals 206, take away T, 2000, times delta S is 214.5 as joules, so as kilojoules that is 0.2145. Okay, so when I do this equation, I'm just going to work that out first. So 2000 times 0.2145 equals, so that is 206 take away 429. Okay, so delta G, I can see that this is bigger than this, so delta G will be negative, but let's just work that out. 429 is minus 223 kilojoules per mole. So because it's negative, this reaction is feasible. Okay, so the value for the delta G is minus 223, so I have confirmed that it is feasible at 2000 Kelvin. Okay, the last part of this question is following on from this. What's the minimum temperature for the reaction to be feasible? So we know that for anything, for it to be feasible, delta G has got to be equal to or less than 0. So when delta G equals 0, delta H equals T delta S. So we can substitute 0 in there and then rearrange this equation. So delta H equals T delta S. What's the minimum temperature? So we need T on its own, so T equals delta H over delta S. We have delta H, which is 206 kilojoules. I'm going to put it into joules, divided by delta S, which we've got at 214.5. Okay, so I just need to plug that into my calculator. 206,123 divided by 214.5 equals, that's, oh, I can't even see that, I'm going to do that again. 206,123 divided by 214.5. Do you know what? I don't even know why I've put that into joules. I think I just need it in. No, that's right. That should be right. Okay, I've got a figure of 9. I can't read it. It's 960.37. So 960.4 Kelvin. Okay. So that's in joules. That's in joules. And if I can read my calculator, 960.37 to 960 Kelvin. Okay, so number 7, the enthalpy change of vaporization of liquid cyclohexane to gaseous cyclohexane. It wants the entropy of that change. So I always like to draw these things. If you don't know what cyclohexane is, you could put X liquid to X gas, but cyclohexane is a 6-membered ring, and that's as a liquid, and it's going to cyclohexane as a gas. We know that the enthalpy change of that, which is vaporization, I've probably written the wrong thing, but we know that that is plus 30 kilojoules mole to the minus 1, and it boils at 81 degrees C. Now that requires moving into Kelvin, so we need to add 273 plus 81, and that will give us 354 Kelvin. Okay, so calculate the entropy change of the system. Okay, so as this boils at 81, basically we've got the delta G is 0. Okay, so delta G equals delta H minus T delta S, but at this phase change it just takes place at the boiling point, so it becomes feasible at the boiling point, so delta G is 0. Okay, so what we have is delta H equals T delta S. It's requiring us to calculate the entropy to calculate delta S, so we'll get delta S on its own, so delta H over T equals delta S. H it's given me, T I've just worked out, it's given me as well, so I can work this out. So it's 30 kilojoules, but we know entropy's in joules, so I'm going to change this to joules. So 30,000 joules divided by 354 equals, and so I'll get my little calculator here. So 30,000 divided by 354 equals 84.7 joules per Kelvin per mole, and you could round that up to 85 joules per Kelvin per mole. Okay, number 8 and 9 require you to draw a graph. So you'll need graph paper, or if you haven't got graph paper, you're going to have to draw yourself some scales, which is what I've done. Okay, so you're going to have to plot delta G against T. So I have done that. I've got my scales here. So this is delta G, this is T. I've plotted the graph, the points, and I've drawn a straight line graph, and it's intercepted here. I've actually used my ruler, so I think I've got 1 centimetre per 200 here, and I've just worked out what that measurement is, and it works out around about 230, but depending on really how accurate you've been in getting your plots, I'd allow plus or minus 10 on that value, so anywhere between 240 and 220. So at this point here, this is the enthalpy of the reaction, because when T equals 0, delta G equals delta H. So we can always delta G equals delta H minus T delta S. So when T equals 0, this value here becomes 0, so delta G equals delta H. So this value here is delta H, so 230 kilojoules per mole. So that answers the first question here. So plus 230 kilojoules per mole, and it has to be plus. You have to say plus. It's on the positive side of this axis, so it is plus. Okay, so you have to put the plus sign. It says from your graph find delta S of the system. Well, that's just a straight gradient, and all I've done is I've actually used the points they've given me, because obviously my graph isn't so fantastic, but I've used those points that they've given me here. So at 400 the temperature was 145, and at 1600, sorry, the delta G was 145, and at 1600 the delta G was minus 78. So if I work out that distance there, that will give me the change in G, and if I work out the distance between these two, that will give me the change in T. So the delta G over the T will give me delta S, basically. So if I work this out, so 145 and 78, 145 and 78, that distance there is 223, so 223 divided by the change in temperature. Actually, that's what that should be. So that's 1600 take away 400, which is 1200, and I just put that into the calculator. 1200 equals the delta S works out at 0.1858, and I'm just going to check that that is the case. 223 divided by 1200, 0.1858. Okay, we know that that's in kilojoules, so this would be kilojoules per Kelvin per mole, but if you wanted to put it into joules, you multiply that by 1000, and that is 185.8 joules per Kelvin per mole, and I quite happily accept 186. Your gradient will be either side of that, so if it's round about 186, then that's fine. I just realised I haven't shown you the working, so I'll show you down here. So delta G, the change in delta G divided by the change in T gives me delta S. So 223 divided by 1200 is 0.1858 kilojoules per Kelvin per mole. If I want joules per Kelvin per mole, it's 185.8, or I'd accept about 186 if you're going to round it up. So anywhere between about 200 and 170. So if you get somewhere in between there, you're in the right ballpark. Okay, so the answer here then is 186 joules per Kelvin per mole. Okay, and this is the stretch and challenge question. It's no different really than the others, but you do have to have a little bit of a think about it. The following reaction becomes feasible at 5440 Kelvin. So basically the delta G is 0, and the temperature, that's the feasibility temperature. So if we do delta G equals delta H minus T delta S, we know that this becomes feasible. Well, then delta G is 0. Okay, so with this particular question, we've got the entropies here, and we can substitute into this equation. So it says calculate the entropy change for the reaction. So we've got the entropies given here. We know that the entropy change is the sum of the entropies of the products, take away the sum of the entropies of the reactants, and the products are oxygen and hydrogen. Oxygen is 2O5 and I've only got half a mole, so times a half, plus hydrogen. Hydrogen is 131. Take away the sum of the reactants. The reactants is water gas. Water as a gas, 189, so 189. And I can put that into the calculator. So 205 times 0.5 equals plus 131 equals, take away 189 equals, so that is 44.5 joules per Kelvin per mole. Okay, calculate the value in units of the enthalpy change for this reaction at 5440. So we know that this is feasible at that temperature. So delta G will be 0. So we want the enthalpy. So delta H equals T delta S. So here, if delta G is 0, then delta H minus T delta S is 0. So delta H equals T delta S. Delta S we've got, T we've got, so we only need to work out H. So T is 5440, and the delta S is 44.5 joules per Kelvin per mole. So if we put that into the equation, 5440 times 44.5 equals 242,080. I'm going to divide that by 1,000, and that gives me 242 kilojoules per mole. So 242 kilojoules per mole. And then finally, the standard enthalpy of formation of water is minus 286. Using Hess's law, calculate the enthalpy change for the change liquid to gas, water liquid to gas. So I'm going to write this out again. H2O liquid goes to H2O gas, and it wants me to it's giving me the standard enthalpy of formation of water. So I know that that is forming water from its elements. So the elements that I will be using are hydrogen and oxygen, if we want to put those there. So I'm going to be making liquid water out of hydrogen and oxygen, and I'm going to be making gaseous water out of hydrogen and oxygen. And it wants this standard enthalpy of formation. It wants this enthalpy change. So that's what I'm going to be calculating. Here, standard enthalpy formation of water, so that's liquid water, is minus 286 kilojoules per mole. I have just worked out the enthalpy for this for the elements to the gas. So that is minus 242, because we're going from the elements to the actual compound, so that is negative. So then if we work out Hess's law, delta H equals, so if that's one root, and I'm going to go to the this side by this route, so I'm going against the arrow, so I'm going to change the sign, so plus 286. I'm going with the arrow, so I'm going to keep the sign the same, 242. Oops, let's just move that over so you can see that. Okay, so we add those together. So 286 take away 242 equals 44 kilojoules per mole. So the latent heat of vaporization, or the enthalpy of of vaporization is 44 kilojoules per mole. Okay, so I hope that's been a little bit of feedback for you on that AFL task that I had set. Just remember, you can always email me if you want any further explanation.